I am now recording. So in terms of things coming up, Monday, your next formative assignment is due. And that is, let me pull that up because it might merit a bit more explanation than typical because of the different format. So it is a Word document that is posted on the website at the Formative Assessment 3 due date, and it's also linked from inside assignments and icon, and it's a sheet that looks like this. So what I'm looking for is for you to break down these equations and figure out which terms represent what and how what they mean changes as a function of progressing across models. So just as an example, if I were to look at a single level empty means model here, so for cross-sectional data, the idea that each person has one y and one e, which terms in this model equation are fixed effects? Oh, can I share screen? You bet. Wouldn't that be helpful? Infinitely more helpful than me narrating through space.
We can pull it up on our computers, but yeah, if you're pointing.
Yeah, you can see my mouse move at the very least. I've trained myself to stop gesturing at the screen and to use the mouse instead, but you know, I'm still got a ways to go, clearly. Anywho, in this little equation here, what are fixed effects?
Beta sub 0.
Yeah, so we would write down beta sub 0 in this box. And what does it mean in this case?
The unconditional mean of means?
Yeah, it's the grand mean or the unconditional mean. And so then the question would be, what terms are fixed effects in these models, and how does what they mean change as a function of what else is in there? And so I'm looking for you to identify the fixed effects, the terms that will have level 2 variances, so those would be the random effects, and then the terms that will have level 1 variances. And as per our usual, we will go over this in class, and I will post an answer key once we're finished so that you can compare your answers to what I wrote down. So try to do it as best you can from memory, but if you need to go back to the notes, of course, that is fine. So any questions on this little activity? Due Monday night. 2 points for giving it a shot. All right, then hopefully that will go well. Your next homework is not yet ready, but it should be within the next couple days, and I will send an email out once that is ready. And it will be based on example 5. You get your first chance at running multi-level models that have fixed and random slopes, doing it using both maximum likelihood and residual maximum likelihood estimation to see what changes across those estimators and what stays the same. So that will be our plan. So any questions on logistics or any stuff like that? No? Good so far? So far, so good then. All right, so where we were last time is looking at the random linear time model. So the model equation, the last box on your formative assessment 3 activity, has 2 different sources of between person differences. We got U0 right here, which is our random intercept. That allows each person their own intercept deviation at wherever time 0 is. And U1, which is the new idea, a random slope. So broadly construed vocabulary words, the word fixed means everybody gets the same. A fixed effect is an estimated constant. The word random, in this context, means everybody gets their own. So rather than estimating a separate U0 and a separate U1 for each person, what do we estimate instead?
Variances.
Yeah, there are variances across people. So that means in terms of estimating the model parameters, we only count the variance rather than however many U0s that would work out to be. Otherwise, the more people we add, the more things we'd have to estimate, which would not go well. And we started looking at what this model predicts in terms of the pattern of variance and covariance. And I believe we came up with this V matrix right here, in which V is what? We'll do a little vocabulary review. What does V represent? Yeah, G and R combined is the way I would say it, because plus you'd have to put air quotes around to make the math work, but G and R combined. So V is the idea of once we put the levels back together again. Because really the idea of dividing terms into level-specific variances and covariances is a hack. It allows us to create an overall pattern that better describes the variance and covariances over time, and that overall or marginal put back together again is in V. So level 2G, level 1R combine to make V, but there's another set of matrices that have to work to make the math work, and that's what I'll show you today. But in this example, the pattern that is predicted by adding the random linear time slope is variance on the diagonal that increases over time, covariances and correlations that change over time. The occasions that are closest together are predicted to be most related, but they're not in a lagged pattern. So remember previously, like the AR1 models and the Toeplitz models, those would have said that like the off diagonal is the same all the way down. That's not the case here. So it's a different kind of pattern, but it is nevertheless a pattern. And I think where we left off with was the idea of how do we talk about effect size for random effects. So I am of the opinion that the idea of R square or pseudo R square when you're talking about the contribution of a random effect does not make sense. Because the whole idea behind R square is explained variance or variance accounted for. But conceptually speaking, random slopes are error terms. We don't know why each person changes differently. So it's not like we've explained it. We've just said part of the error is attributable to person slope differences. Part of the error is attributable to person intercept differences, and part of the error is attributable to the ease relative to the lines that are being predicted for each person. So 3 different sources of error to be predicted by time invariant predictors. So person level things will predict the random effect variances, and time level things will predict the E variances. So we looked at a new type of confidence interval to try and describe the extent of random variation, and you'll be asked to compute this in your homework, as well as other indices of reliability that are built on the classic idea of true relative to true plus error, where the error part is approximated by the residual variance for the intercept reliability, and that rescaled by the amount of variance in the time predictor. So this little jobby right here, that is the variance of the level 1 predictor that the random slope is for. So you would need to go into your data set and find what the variance is of that predictor to plug it into the formula. In the code that goes with this example online, I have done that for you first thing. I ran descriptives on the time predictor to get its variance so that you'd know where that number came from. And I have an Excel spreadsheet that goes with the download packet inside there where I have all of the calculations built into spreadsheets, so you can just plug in your numbers. Or you can use whatever package or method you want to compute things. So there's relatively few things I would ask you to compute by hand. This happens to be one of them, but it should be relatively painless. Okay. How are we doing so far? Is this sounding familiar? It's Thursday. I should say happy Thursday. Since it's only been 2 days, it should be more familiar than over the weekend, perhaps. So we had a question at the end of class, which was basically, how do I know if this is good enough? So we have this random linear time model. We want to somehow compare it against the data, ideally, but we are unable to do that directly if we're using residual maximum likelihood as our estimator. Those models are used to compare alternative models for the variance if you're in REML, whereas alternative models for the means will have to be compared in a different way. So I will get into the idea of how to test what is known as absolute fit in the next unit, Unit 6, where we talk about nonlinear change. And I will have 4 different types of models fit to the same data, and we'll go through practice in doing that. But for now, what we can continue to do is the same idea of adding things and seeing if it helps. So we started with an empty means random intercept model, which you can always estimate regardless of whether your occasions are balanced, regardless of whether they're equal interval, so long as you've got at least 2 for at least some of the people. Then we added fixed linear time. We get to stare at the p-value that goes with that wald test to see if that helped the model. It did. Then we added random linear time. And how do we test if random things help the model fit better? What do we have to do to answer that question if a random slope helps the model? It is right here. Likelihood ratio tests. a relatively new concept in this class, but if you've seen this before in generalized linear models, structural equation models, a whole bunch of other contexts, it's the idea of comparing differences in height. So the log likelihood from a model with fewer parameters versus a model that has more parameters, times -2 for the difference. So the -2 times log likelihood for each of the models here, the difference between those two numbers is 48 on 2 degrees of freedom, because when we add a random linear slope, what are we actually adding to the model? What are the two things? Two things. What goes into the degrees of freedom? You're nodding, yes, it's 2, but what are they?
The variance for the random slope and
Yep.
the covariance between random intercept and random slope variance.
That's it, the variance of the random slopes and the covariance between the random slope and the random intercept. So as a more general principle in multi-level modeling, anytime that you add a random effect to a level, you should also be adding a covariance with all the other effects that were already random at that level. So this model has 2 levels. The top is persons for level 2. Because we already had a random intercept across persons and we're adding a random slope, those 2 random effects get to be covariate. In, say, 3-level models, if you added something to level 3, it would not have a covariance with anything at level 2 or vice versa. So it's always level-specific terms that get to have a covariance. And nothing ever covaries with level 1 also by definition. So this improves the model more than the critical value of about 6-ish. So yes, we would say that we keep it. Here are ways of describing the effect sizes for both of the random effects, so we can try to convey in the metric of the original outcome just how much variability those random intercepts and slopes imply relative to the fixed effects as the middle. Okay, so moving on then. Based on my original pictures, so for now that's what I'm going with, is literally an eyeball test. Where are they? Here they are. So this red line shows the trajectory of the saturated means over time. That looks pretty darn linear to me. So on the basis of this picture, I'm going to say linear is probably good enough. The variances by wave have a not linear pattern, but it's actually quadratic. It's harder to see it because there's only 4 points, but I know that for a fact because I generated these data using a random linear slope model. And what we'll learn today is that anytime you add a random linear slope, you are adding heterogeneity of variance in a quadratic or U-shaped pattern. So this is like the right half of the U that this is showing right here relative to this as a minimum. But what we don't know yet is whether or not the variances and covariances are adequately recovered by this. So it looks sort of like the variances might be if I were to plot the predicted variances against these ones, but the covariances are still somewhat up for grabs. So what we can potentially add still, without heading into nonlinear slope territory, which we haven't described yet, find where we were, is stuff in the R matrix. So the random linear time model that we fit has this kind of R matrix right here to it. I would call that independent or diagonal or VC for variance components. It says that the variances are the same across time for the E's. That's what we're talking about specifically, the variances of the level 1 E residuals, and that there are no E covariances. So that's a pretty strong statement. It's saying that all of the reasons why the occasions were correlated are over here in G. And what's left is just like it would be in a standard general linear model, E's are independent. So we can test that by adding patterns to this R matrix and seeing if it fits better. The same patterns that we did 2 weeks ago or last week, the ACS models. So I've got 2 examples of that. So I'm on, let's see, the bottom of page 11 here, where I am adding an auto-regressive residual correlation in R. So in the code, what I would change in SAS first, the repeated line controls the pattern that's in the R matrix. I am changing it from VC to AR1. This is the version that assumes equal interval time, by the way. There's a different set of codes for the unequal intervals, but in this case, that's fine. And then I'm setting up a likelihood ratio test relative to the model that doesn't have that autoregressive residual correlation to see if it helps. In Stata, it's residuals AR1 right here that I'm changing. It used to be independent right there. And in R, I have to use LME only. So the previous examples in R up to this point, I had shown the model two different ways, using the LME function within NLME and using the LMER function in a different package, which is LME4. The latter, LMER, ironically, adding the R means it takes away the R. Seriously, in LMER, there is no R matrix. It's diagonal and you don't get a choice. How's that for counterintuitive naming? So I'm only having LME because that's the only way that I know how to do it. And we've got the correlation structure here added to the R matrix. So this is similar to what we saw in the previous unit. And using ANOVA rather than RANOVA, because ANOVA works with the NLME package and RANOVA works with LMER. And yes, I had to figure out all of that by trial and error. I was not born knowing these things. So here's what we end up with for our new R matrix. So the AR model is phrased directly as a correlation. So the AR coefficient was estimated as the 0.018 that's on the first off diagonal here for the lag1 correlations. That 0.018 squared is how the second off diagonal got made, and 0.08 to the third power would be the last one. Now those numbers look pretty small. The table that lists all of the estimated parameters in the model for the variance lists it directly. 0.02, wait a minute. Oh, I was highlighting the wrong table. It's right here. It's in R core, excuse me. R is covariance, this is correlation. My bad. But still a very tiny number. So in this case, I would say it might be reasonable to stare at this p-value because technically speaking, the autocorrelation could be negative. It's not bounded at 0 the same way that variances are. But a safer bet is whenever you are adding or subtracting things to the model for the variance, that's some kind of likelihood ratio test. So that's the more general way to test whether things help the model. Likelihood ratio test for any new parameters related to variance and covariance over time. So this p-value suggests that that autocorrelation is not different than 0. The likelihood ratio test agrees with me. The p-value is nearly the same, just a little bit off in the third decimal place. But the difference in models, -2 log likelihood, is very, very tiny. So no, that does not help. Another choice that might be reasonable is Toeplitz, where I am adding just a lag1 residual covariance. So just the adjacent occasions are allowed to have a covariance for their level 1 E residuals. So that one is fit in SAS as TOP2. The first one is the diagonal. The second one is lag1. It is also possible to do that in Stata, and it's called Toeplitz 1 in Stata, and it's not a predefined structure in R. So we try that one. It is phrased directly as a level 1 covariance. And so note that it doesn't extend to the other off diagonals because Toeplitz is the one that isn't squared or cubed. It's just separate ones for each off diagonal. Same thing here. It looks, if I just eyeball the p-value, that that's not going to help. Likelihood ratio test agrees it's not going to help. So I can't think of anything else that would be reasonable to test here. One thing that I see people do that I would say be very cautious if you want to try this in your real data is to test heterogeneity of the level 1 residual variances. This is baked into SEM because that's the default when you set up these sorts of longitudinal models using structural equation modeling software. The level 1 residuals have a different variance at each occasion. But here's the thing. In our model, the random slopes also create a different variance at each occasion already. So there's a sense in which allowing the E residuals to have a different variance at each occasion is redundant with what the random slopes are trying to do. And if you don't have a lot of occasions, they tend to cause convergence problems when you try to do both at the same time. So I would caution you against a default strategy of letting these E residual variances be separate, because that's the job of the random effects. Their job is to build in the heterogeneity across time. So I'm not going to try that one for that reason. And the rest of this, I'm not going to go over in class because this is a whole lot. But this is going to be a separate recording that I make from my basement for the folks who are either in the SEM class simultaneously or who are familiar with those models, so that you can see how this exact same set of models would look that way. The only catch is that when you use SEM software, you are forced to use regular flavor maximum likelihood. And so that's going to result in variance components at level 2 for the random effects that are too small. If the variances are too small, that means the corresponding standard errors are too small. And if the corresponding standard errors are too small, what happens to the corresponding p-values? Too small, meaning type 1 error is too high. So the use of SEM software usually implies that you have enough people to make that distinction moot, to where the results would converge to basically the same numbers, regardless of whether you're in regular ML or the residual version that's better for small samples. And if you want a results section that goes with this example, that is in chapter 5. So the end of that chapter in the textbook has words that I would use to describe all of these things. Okay, so any questions on the syntax and output? Because that's what you'll get a chance to practice with your next homework. How do we know how many people are enough for SEM? That's a great question. There is a formula, and I cannot do it off the top of my head, but it has both the number of parameters and the number of people in it, and you can actually compute by how much the results would change given your particular model. It's in chapter 5, and it's in one of the slides that were coming up today. I would say, practically speaking, for models like with this level of complexity, maybe 50-ish, but you can't really give just one number because it depends on how complex the model is. The more parameters there are, the more of a difference there's going to be. So I know that's a dissatisfying answer, but I hesitate to just give answers and not have it be contextualized by it depends, because it does always depend. Okay, other questions? Everyone's quiet today. Are we okay on a Thursday? Beautiful fall afternoon? No. They're like, no, we're not. I'm just going to stare at my laptop. See, if I stare at my laptop, I'm still looking at people. It's a joke, folks. Tough crowd. Dang. All right, well, how about we do some matrix algebra, because that always makes things better. Now, here's my promise to you. I want to show you this, but I'm going to emphasize the big picture, and I'm not going to make you do any of the math. Fair? We're going to get the programs to do all of the math for us. But I think it's important to understand the pieces that are involved in how this complex pattern gets put back together again. So I am on slide 25 here. That's where I'm starting in lecture 5. So we looked at this last time. This is summarizing just where we've been up to this point in terms of adding effects of time. Adding a fixed linear time slope first to the model for the means, which allows some kind of average change, and then adding random linear time slope, which allows individual differences in change. So conceptually, what that does is allow us to answer two different types of questions. Are people changing on average? Like, did kids grow? Or did the treatment work? Those kinds of basic questions. Is there change? That's fixed effects. If the change is nonlinear, we're probably going to need more than one fixed effect, such as a linear and a quadratic slope, or an exponential slope where we have amounts and rates instead of just lines, or piecewise models, which is like linear splines where you have like two different slopes. That might correspond to like an intervention design where something different happens in the middle, like a before and after kind of thing. So questions about average change, that's fixed effects. Questions about which fixed effects need individual differences. Do people change differently? That's random slopes. And every fixed effect has the potential to have a random effect that goes with it if you have enough occasions. What enough is something we'll talk about in the next unit when we get to alternatives for nonlinear slopes. So what's happening under the hood then? When we add random time slopes to our model, we are going from a model that has 2 piles of variance to a model that has 3. Another way to say this is that our model is now allowing 2 distinct kinds of person dependency. Random intercept is a constant person dependency due to mean differences. Random slopes for time creates a non-constant person dependency because of individual differences in change. So we have then a 2 by 2 level 2G matrix because we have a variance of the random intercepts at row 1, column 1, variance of the random slopes at row 2, column 2, and their covariance right here. And then for the sake of right now, we'll say that our R matrix is diagonal, but just know that this is a choice that you can make. You can add stuff to it if it's warranted by the data, do the likelihood ratio test to see if it helped. So what's cool about this is that these 2 things put together again can work for people who don't have all of the occasions. They can work for people who don't have the same occasions. So you don't need balanced time, you don't need complete data, and you don't need interval data. It's very, very flexible. So one of the consequences then of adding this random linear time slope, this idea that people have different slopes, creates heterogeneity of variance over time. It implies that there's going to be some occasion at which the variance across people is at a minimum, and on either side of that, the variance across people is going to increase. It's a U-shaped function that this model is actually creating. Now, where that comes from is what I want to show you next, but this is the big idea. Variance increases relative to a minimum as a function of this model. So, boiling it down to how this new random linear time model predicts the variance at any one occasion. This is in chapter 5, by the way. So if I want to compute the model implied variance at a particular occasion, here's the model that I have. Anything that is a fixed effect drops out. So all I have to do is figure out the variances that have to do with the random or residual terms. So that's this. If I distribute this variance operator across, I end up with the variance of the random intercepts as the starting point. I end up with the variance of the random time slopes, and I also end up with twice their covariance, as well as the residual variance. So rearranging and combining terms, the part in blue is the point that I want to make here. The variability that this model predicts across time depends on which occasion it is. And it's a function of the random slope variance multiplied by time squared. And that's where we get the U shape in terms of how the variance is predicted to change. It's literally right there in the squared term. Otherwise, without that random time slope and its accompanying covariance with the intercept, we're stuck with just the parts that are outside the blue here. Random intercept variance plus residual variance. So that part is just from the random intercept compound symmetry model. So the blue part is what's being added by the presence of this random linear time slope. Another thing that's cool about this, previously in the ACS models, what were our choices with respect to variance? There were only 2 choices, right? The variance across time was either all the same or each one was different on each occasion, right? So that meant like if you had 5 occasions, you had to estimate 5 separate variances or 1. And those were your choices. So this adds a different type of choice. It's a function. So in terms of the number of parameters that are being estimated to create this function, there's only 4. Intercept variance, slope variance, their covariance, and e-variance. But that then predicts a different potential variance that's constant due to this function. So you don't have to have separate numbers for time 1 and time 2 and time 3. The function describes how variance changes across time. So that means that people who have time 1.5, there's a predicted variance at time 1.5 through this function. People who have time 2.87, they have a predicted variance at time 2.87. So it allows us to interpolate across time because the variance changes as this function rather than estimating a separate variance for each discrete occasion, which requires balanced data to do. So it's really cool how this works, I think, in a nerdy kind of way. Same deal with the covariances on slide 29 here. What it boils down to is that the predicted covariance between any 2 occasions starts with our friend random intercept variance, which is what we had from compound symmetry before. If we only had a random intercept, then the model says the only reason why 2 occasions were related is because of person mean differences, and that's it. Now we're saying it's person mean differences plus the part that's in blue, where the predicted covariance depends on which 2 occasions it actually is. So this is the way that those off diagonals in the V matrix get predicted. It's this function. And it's the same idea. Because it's a function, we can predict what the covariance would be between any 2 occasions, regardless of whether they're actually observed in the data. Interpolate. I think that's the right word, right? I get that one and extrapolate combined. Any word wizards here that can tell me which is which? Is interpolate the right one? No one's willing to tell me I'm wrong. Yeah, okay. It's interpolate, fine. I bombed my GRE verbal section. I'm not too proud to say that. It's interpolate. I think that's an actual word, though, as opposed to the words I make up. So here is, then, what it looks like to describe all the things that I just said, but building up from the idea of matrices instead. So in describing how this model works, each person gets their own set of matrices. Each person has a Y that holds all of their occasions. They have an X, which is the design matrix that holds the predictors that have fixed effects. So here, what's the column of 1s for again right here? What does that go with? That goes with the fixed intercept. So that gets multiplied by gamma 0, 0. And then this second column is going to be like time. So in our example, it was just time 0, 1, 2, 3, which gets multiplied by the fixed slope. And now over here, Z looks the same as X in this model because all predictors that have a fixed effect also currently have a random effect. The reason that there's 2 separate names for them is because that's not always true. You can have fixed effects of predictors that don't have random effects with them. Can it go the other way, though? Can you have predictors that have random effects that don't have a corresponding fixed effect? You cannot. The fixed effect is the middle. So if you leave it out, you're saying it's exactly 0, and that will often cause convergence problems and interpretation problems. So even if it's not significant, I would leave it in. So the new column right here, the second column in Z, is what we're focusing on. That's the new random slope that gets multiplied by the UI random slope for this person, and then E picks up the residuals. So when you multiply this out, it looks a lot like the models in the way that we've already written them. Now the predicted variance and covariance. I said earlier that G and R combine to make V. This is how it actually works. G is not the right size to be added to R directly, so we got to fix it. So the Z matrix, and again, that is the matrix that holds the predictors for that person that are to be given random effects, is in front of G, and its transpose, which is like just kicking it over onto its side, is behind it. So if you work out the math, then we have a 4x4 matrix that's a result that we can add directly to R, and then that makes V. And I have what the diagonal would be here and what the off diagonal would be here, because it's very hard to put that all into one giant matrix and show the predictions. But this is the key idea, is that the way that the random effects get applied depends on what data you have. So this is for somebody who has 4 occasions, where the 4 occasions are perfectly balanced and complete the way they were supposed to be. But what if that's not the case? So how the giant V matrix gets combined across people would look like this. This is an example for 2 people. So the purple box here, that's for the person that we just looked at, where they have 4 occasions that are balanced, they came in when they're supposed to. Now here is the data for another person who also has 4 occasions, but they're off. No worries. They still get those values multiplied by the same parameters in my G matrix, my random intercept variance, my random slope variance, and its covariance. And then we add the same residual variance. So when this all is said and done, each person gets their own V that's based on when they were observed and their observations only. When everybody doesn't have the same potential V is when we don't have the capacity to test absolute fit. If V has a different set of observations going into it, we don't know what the right answer is. If everybody has the same occasions, we could see what the right answer is. But this allows us to at least estimate the model, even though not everybody cooperated. And the same is true if I had missing data. So in this slide 33, my second person here only has 3 occasions. Okay, cool. Their contribution to the giant V would only be a 3x3 instead of a 4x4. So the big picture here is that the way that these models handle missing data and unbalanced time is by allowing each person to have their own place on this function of heterogeneous variances and covariances based on when their times were actually observed. They don't all have to be the same because the model doesn't work like that. Now I do want to point out one thing I skipped on the previous slide. So the purple boxes are highlighting a pattern that's known as block diagonal, which is like stuff and then zeros everywhere else. Now, why do you think we would have zeros on all of these other places here that are not in the purple boxes? What is that saying?
Trying to identify each person.
Say that again?
I'm just trying to identify each person's data set.
Each person, yes. But what are we saying across people with all of these zeros stuck everywhere?
They are independent.
They're independent. So in terms of what our model is assuming, we are focusing entirely on how people affect the dependency over time. People are independent according to this model. Now, what if that's not the case? Can you think of examples when people would be dependent instead of independent? Clustered data. Kids in classes, siblings in families, physicians in hospitals, take your pick, right? So the way that we would build the model to include another layer of dependency is to put stuff in these off diagonals. We'd put in additional layers of random effects that would then induce a correlation of people who come from the same sampling unit at level 3. It's really cool. It turns out that those models are actually way easier because you don't have to worry about time. In those cases, compound symmetry random intercept only is a reasonable place to start, and what would have random slopes would be people predictors rather than time predictors. So the dependency of observations within a person is really what this is focusing on. People are still supposed to be independent. Otherwise, we'd need another level, or we need to put in fixed effects to control for whatever relationship people have with each other. All right. So big picture here. Along the continuum of compound symmetry, There is a relationship over time, but it's constant and unstructured. I don't know, but everything gets to be what it wants. This idea of adding in random slopes puts us somewhere in the middle. What it's hopefully doing is creating a pattern that matches what's in unstructured, but using fewer parameters to do so, and not having to estimate separate variances and separate covariances using a function to allow them to be heterogeneous over time as needed. That's the big picture. The only time that we can compare against unstructured to see if we've done a good enough job is balanced data. Otherwise, we would not have one common matrix that would summarize everybody. And it doesn't work. Yeah. Okay, how are we doing? Not so bad, right? If you keep the big picture in mind, that's really all I need. The big picture is adding random slopes makes the variance and covariance change over time in a function. That's it. That's all I want you to hang on to. The details of how it works is right in here. And to be honest, I did not understand any of the details for probably 10 years after I started learning these models. It took a very long time to wrap my head around all of it. All right, so we talked about effect sizes. This is the idea of random effects confidence intervals, which we did, and I showed that to you in the handout, so I don't need to belabor that point. Same thing with intercept reliability and slope reliability. Those are the same formulas that are in the handout as well. Moving along then, so a broader, saying the idea of dependency a different way. So when you see people describe the benefits of using multi-level modeling in particular, one of the phrases that you'll see people write is that multi-level models handle dependency. Handle is a word that people use when they don't actually know what they're talking about and they just want to wave their hands. It's true. Full information maximum likelihood handles missing data. How? Handles it. How does this handle dependency? It handles it. Well, this idea of random effects, I want to try and link this idea together of what they're trying to do with respect to dependency. So the types of dependency that we've seen up to this point, why would occasions from the same person be related? That's the question. Dependency means correlation. Mean differences across people, that's what an intercept is for. Differences and the effects of time-varying predictors, that's what random slopes are for. Or just occasions are more related the closer they are in time. That's what autoregressive, topolets, and other similar types of patterns are for the regressive, for the residuals, excuse me. So another way to say all of this graphically is once upon a time, there was an E. Like just one pile of variance in all the data before we did anything to it. And the very first thing that we did is split that E into two sources. We gave each person their own person mean rather than starting with the grand mean as our naive jumping off point for a model. And we did that by giving each person a random intercept, which is how far they deviate from the grand mean. And we have the variance across people in those random intercepts as the level 2 between person part of the model. And we have the E's that are then left over. So the definition of E changes across this, right? E used to initially represent all of the difference between the grand mean and that person's outcome at a particular occasion. After we take out the random intercept variance, put it in the G matrix, then the E's that are left, whose variance is in the R matrix, are the difference relative to just the person mean parts. So they're lesser. And if you add the random intercept variance and the residual variance back together again, it'll be pretty close to the total variance you started with. It won't be exactly the same, but it'll be reasonably close. So this is a partitioning of variance into levels that in turn allows the E's to be related because of this U. So what was the relationship is now over here at level 2. Then we added fixed linear time. Which of these two piles of variance should fixed linear time explain? Level 1 residual level 2 random intercept?
Level 1.
Level 1, yeah. So if I use like a Venn diagram and like think of like the predictors like accounting for some of the variance, part of what was E is now accounted for by this within person effective time. Once we do that, the intercept variance is going to increase, at least to some extent. So then we have the question, all right, so is one slope good enough for everybody, or do people need their own? And where that potential for people to have their own slopes comes from is still E. This residual variance at level 1 splits again. Because part of the reason why we might have had the differences relative to the line is that it's not the right line. Your line needs to be steeper, your line needs to be flatter, and once you adjust for that, the e's should be smaller relative to your new, better fitting line. So part of what was attributed to level 1 residual time-specific variance is actually not time-specific. It's time general, because this person has this general tendency that's playing out across all their data. It's a person characteristic. So we extract that person characteristic, and that shows up at level 2. And so the intercept variance then just comes along for the ride, but it changes interpretation to be specific at time 0. So when all is said and done, we have 2 different reasons why the e's would have been related. 2 different types of person dependency, and then the e's that are left are supposed to be unrelated. Now, where could this go wrong? What if the line that we drew shouldn't be straight? Could that happen? Do people change forever and ever and ever? Probably not. They slow down at some point, either because of measurement ceilings or just because of the end of a natural process. So what if we needed to make a bendy line? Could we do that? Add, like, just as a simple example, take time squared and make the line a little bit more U-shaped. Which pile of variance is that going to explain? Where you got 3 choices here. You vote for 1? Is that what you said? Or you want to take it back?
I would say that between the slope variance.
So we have maybe this or maybe that. Not sure. Anyone else want to play? So the question is, if I add a fixed effect of time squared, which of these 3 is it going to reduce? I've got level 1 time-specific variance. Level 2, why do people change different variance? Level 2, why do people start out different variance? Let me say it another way, since I feel like everyone knows this, but you're being shy, right? No one wants to be wrong. So if I have time that's not squared and it explained E variance, if I take time and I square it, what's it going to explain? The E variance. Yeah, it's not different. E variance is, why are you off your line today? Well, because I need a bendy line. You gave me a straight line. That's why. So if I add time squared, then this E variance should go down further. Now, what if people need differentially bendy lines? Like some people level off more than others. Could that happen? Certainly. Where's that going to come from?
The slope variance.
Oh, we got 1 vote for slope variance.
Yeah.
2 votes for slope variance. Anyone else want to play?
So I just got here, but could you fit like a quadratic or a not linear term?
That's what we're talking about. I'm talking about a random quadratic, a random slope for time squared. It has to come out of one of these 3 variances, because variance cannot be created nor destroyed like matter. Even if it's destroyed, it's like explained, right? Destroyed seems a little bit like much for that term, but it's actually going to be E again. Because it's the same idea. Why are the E's off the line? Because you need a better line. If you draw a better line that fits each person's data better, give each person their own flavor of bendy, the E's get smaller. And then what happens? We have a 3rd light blue circle sitting out here. where people would differ in the extent of their quadratic slopes, in addition to the extent of their linear slopes, in addition to the extent of their intercepts. So the goal of multi-level models as a general principle is just keep pulling stuff out of E until E is empty, until E has no more covariance left to give, and no more heterogeneity of variance left to give. And if not, you can always let the occasions be more related, autoregressive, Toeplitz, whatever pattern to that. But the way that multi-level models handle dependency is by making explicit reasons for that dependency and segregating them into that G matrix. That's what it does. So you are making a very specific statement about what the dependency is. And you don't know if it's been handled necessarily unless you have a baseline to test it against to see if you're right. And that is only true for balanced data. So there's a sense in which we kind of have to stab in the dark a little bit with this. And the only way that you can tell is by continuing to add stuff and see if it helps. Now, why would this matter? It matters in terms of what roles your potential predictors would have to play. So if I had a hypothesis, for instance, that people who entered the study at an older age would start off lower and they wouldn't change as much. Like they wouldn't benefit from whatever my treatment is if you're older. Well, if this is my model, then there's two distinct ways that age could enter. Age could affect the intercept. Age could affect the linear slopes. But if I know that I have a third light blue circle over here, which is individual differences in the extent of bendiness, age could affect that too. So that's three separate things that each time invariant predictor could potentially do. So knowing what all sources of time-related dependency you have is a logical precursor to what the predictors are there to do. Think of it the other way. What if everybody did change the same? What if we added these random slopes and we saw very little evidence that they helped the model? We tried to plot them and they were basically parallel, and it wasn't a power issue, it just looked like people didn't change differently. Would it then make sense to see if age predicted individual differences in change? No, because you don't have any. You can still try, and there is in fact a middle ground that is a vocabulary word that we probably won't get to until the end of the semester, which is systematically varying. And that's the idea that it's not fixed, everybody is the same. It's not random, everybody is different, but it's systematically different as a function of a predictor. Like if you found that the control group and the treatment group needed different slopes, but within group they were homogeneous, that would be systematically varying. Such cases are possible, but generally speaking, if you don't have individual differences in slopes, it doesn't make sense to try to predict them. Question from the Zoomers, is this what happens when there is a need to model both clustered and longitudinal data? That is actually another set of pictures, in which this picture right here, let's focus on the between person parts. This is assuming that people are independent. What would happen if people are dependent relative to each other, like kids in classes, siblings and families, that kind of thing, is that what we would say is between person would actually need to split itself. And it would be how much of it is within family versus between family, because between persons is both. And what is the commonality of people from the same cluster? Do they start out similarly? Because then you would have a split to this intercept variance. Do people from the same cluster change similarly over time? Because then you'd have a split to the slope variance too. I don't want to scare you, but there's a lot more that one can do. But these are like, Lego building blocks. We're just starting to stack them up together. But this idea of just pulling out sources of dependency, making it a new thing and sticking it in the model, like that's how this is handled. So these are all testable assumptions as to whether it helps. It's not always possible to test whether it's good enough, so to speak, against the best fitting baseline. All right, 126. I want to thank everybody. I'm feeling much better now. I came in here all slumpy, all like COVID-y, not because I'm sick, because I just got vaccinated. Now I feel better. So you guys probably feel worse, but I feel better. So thanks for that. I know, it's a lot. So anytime that we add a fixed effect, we're explaining variance. In the same way that you learned in Intro to Linear Models, this predictor accounts for yay much percent of the variance of this outcome. The only catch is that we have to say which variance. Is it a time level predictor? Because then it should explain level 1. It is a person predictor because then it should explain level 2. In contrast, every time we add a new random effect, we are not explaining anything. We are reattributing error to a different level. We are taking what we thought was independent error at level 1 and moving some of it to level 2 to represent systematic error that's systematic to a person. But we still don't know why people change differently, so it's still error. It hasn't been explained. Attributable is the word I would use. And maybe that's a semantic distinction, but to me it's not. All right. Okay, questions? In certain disciplines, what I have just said is craziness. There are certain areas of social science where random effects are viewed as not a good idea, and you should do fixed effects instead. I'm not making this up. There's usually at least one person in my classes who comes from a discipline where this is the standard. So for that argument, I want to have this one slide about this. The idea of controlling for dependency is what we're talking about. And the way that I have done that is random effects. The other alternative is fixed effects. Generally speaking, what a fixed effect means is that I am estimating a separate parameter for each person to make an inference about just that person. That's my alternative. So if I wanted to control for constant person dependency due to mean differences, I can either have one random intercept variance as an estimated parameter or n-1 fixed slopes, where I would literally treat person ID as a categorical predictor and put it in the model. And it's n-1 because usually we already have one fixed intercept, and so we only need n to saturate it out. That would equally well control for person dependency due to constant mean differences. What about slope differences? I can either estimate this person by time interaction, which is really what a random slope is, or I can estimate n-1 person by time fixed effect interactions and do the same thing. Either one of these would get me to the end result of handling person dependency. But what they then permit me to do varies across approaches. The reason that random effects are useful is twofold: quantification and prediction. Knowing how much variance is attributable to each different kind of person dependency is useful in a lot of cases. That answers research questions about how people differ from each other. But then being able to say why they differ from each other is really the reason behind random effects. Why is it that some people start out higher? Why is it that some people change faster? We can then put in person characteristics to answer those questions. If I did this dummy code approach, this fixed effect approach, could I then see if older people start out lower after I put in person ID as a predictor? No. I've already spent all my degrees of freedom that differentiate people. So I would have a full set of results as to what happened to person 100 and person 101 and person 102, but I couldn't make any statements about why they're different from each other. So if that's what you wanted to know, that would be fine. Let's say that you're doing something like an N of 1 design where you have like 5 children and you're following them for a whole bunch of observations. People do that very commonly here. That's an example of when a fixed effect model might be preferable, because then you could talk about what happened to child 1 and child 2 and child 3, and you know already that child 1 and 2 and 3 differ from each other in lots and lots of ways, and you're not trying to make inferences about why they differ, you're just saying that they differ. Or you want to be able to make statements like, 4 out of 5 children improved due to my treatment, or something like that. So fixed effects is when the desired inference is that specific unit. Random effects is when you want to know why those differences are there. There is what's known as a Hausman test, and there's a couple other variants of it where they turn whether you should use fixed or random effects into an empirical question. And what that actually boils down to is whether your multi-level model is properly specified with respect to your level 1 predictors. There is an equivalence class to that test. So that's much more of a concern when we have time-varying predictors because it gets a lot more complicated. In the examples that we're talking about this semester, for the sake of just getting through the basic stuff, time is assumed to be entirely within persons. So time 0, 1, 2, 3, 4, everybody's measured at approximately those times. People don't differ in where they start in time. That means that the only type of relationship that I can talk about in terms of time as a predictor is within persons. But if people differ from each other in time, then this gets a lot more complicated because I have to be able to separate out cross-sectional time differences from longitudinal time differences. That's chapter 10, if that gives you a sense of how much more complicated that gets. Did I hear a question? No? What are we doing? Nah. Okay. Let's see. How many of you care about structural equation modeling? Big nobody. I love it.
I do on Zoom, just so you know.
Okay. A few people do on Zoom. So how about then I give this the quick treatment rather than the detailed treatment, and then you can watch the videos that I make on your own if you care more. Does that sound fair? Because I have had questions from students who are planning what to do with their longitudinal data, and I get questions like, well, I have this longitudinal study, and I'm trying to figure out whether I should do multi-level modeling or whether I should do structural equation modeling. And my answer is, yeah, you should. And yeah, you should. No, they are the same thing in many cases. So let me walk you through how they are the same. Because this is what's challenging for me at the moment. I am teaching both of these classes simultaneously. SEM meets after this one. And I have to use different terminology and different parameter labels to say the same damn thing twice. So you'll hear me switch occasionally and forget which class I'm talking to. But just know that my mistake is because it is the same thing. So the connection between what people would call a structural equation model based on latent variables and where people would call multi-level models that include random effects is that random effects are latent variables. There is a reason why I draw circles in these pictures to talk about piles of variance. It's not a coincidence. They are latent variables, which are usually depicted in circles when people show their SEM predictions. So these ideas means that we would set up as many latent variables in our structural equation model as we have random effects. The mean of the latent variables are the fixed effects. The variances of the latent variables are the random effect variances. And the variances of the occasion-specific residual boxes are the residual variances. So here's the connection then. Each U, it becomes an F in structural equation modeling notation. So a measurement model, for instance, that would describe how an item is measuring one or more latent factors would look like this. This mu-looking thing here is the item's intercept. Lambda is a slope that multiplies a factor, which is a subject-specific quantity, and then E is the same in terms of our residual. I is for item and S is for subject in this notation. I is for person and T is for time down here. So here is what each of the models we've looked at would go as in SEM parlance. E-only model with no random effects could be set up like this. 4 occasions, things in these pictures that are in boxes are real. Things that are in circles are pretend, latent. So if I have 4 occasions and I ask a latent variable to be estimated and I fix the factor loadings all to 1 so that each occasion contributes equally, the mean of this latent variable is my fixed intercept, and the variability that's left over down here for my e's is e, because at this point there is no variance to this latent variable. If I add my random intercept, so this is our friend the empty means random intercept model, it would look like this, where the intercept variance is now estimated, and the standardized solution would provide my interclass correlation. This constraint that all of the loadings are 1 here, as the slope that multiplies the effect of this latent variable in predicting each of the observed outcomes, makes this an intercept. So it is a random intercept factor specifically because of the way we forced the loadings to be here as 1. Likewise, by this notation, I'm trying to show that I have forced each of these residual variances to be the same number. They're constrained equal, which would be the typical R matrix that we see. If I want to add a time slope, that's another latent variable. I have to define the time slope using fixed loadings, where the loadings correspond to what the time column would be in my data set for multi-level. So in the example that we just finished, it would be 0, 1, 2, 3 for this. If I only have a mean for this latent variable and I shut off its variance, that's the same thing as only having a fixed slope for time. And once I add a variance over here, that brings us to the model we left off with, random linear time slope, where I add a variance here, which means that I would add a covariance between my intercept and my slope. And the e's down here still are assumed to have constant variance. They're assumed to be uncorrelated, but I could add error correlations between them. And if I put constraints on those error covariances, I could turn that into a topolet structure or an autoregressive structure or whatever I wanted. So putting it all together then, this down here is R. These latent variable variances are G. The Z matrix that controls when people were measured is right here in the loadings. And the total put back together again that we call V in this class, we call sigma in the SEM notation. And when I made the slides for SEM and this class, I literally just had to sit down and change all the notation and all the subscripts, but everything is exactly the same. But this brings up one reason why potentially, you would not want to do SEM. What does it mean that I have fixed these numbers to be 0, 1, 2, 3?
I think that would mean that you're assuming time is balanced for everybody.
Time is balanced. Everybody has 0, 1, 2, 3. What if somebody has 2.5? So it depends on your software, whether you can handle that. If you use M+, they have an option called T-scores, in which you can tell it, take these columns of the data and use it as an individual specific set of factor loadings, which corresponds directly to when they were measured. I have looked for this option in Lavon and I could not find it, which is the R package I'm teaching SEM with. And I do not know if it's in Stata's SEM package or not, but I know that unbalanced data, you must use the T-scores. Another reason why this would not be a great idea is small samples. If you only have 20 people, all of the variances for your random effects up here, your latent variable variances, are going to be too small. When would this be a better idea? When what you want to see grow is a latent variable. So if you have multiple measures of a construct at each occasion that form a latent variable out of those multiple measures, and you want to see if that latent variable changes over time, that's what this is for. You would think that that would be called latent growth curve analysis, but it's not. Latent growth curve analysis is this version on observed variables. The idea that factors could change is either called second order growth curve models or higher order growth curve models, because there's 2 layers of latent factors involved. One that would replace these boxes down here, and then the higher order would be as depicted up here in the level 2G matrix. So that's when you would go to the trouble to fit your longitudinal model using SEM, if you want to do latent variable measurement. So that allows greater flexibility in terms of how you measure people over time. If you're using latent variables, you don't have to give the same measurements at every occasion. So long as there is planful overlap, you can change how people are measured to be consistent with what works at a given age. So you could have measures like A, B, and C at the first occasion, and then B, C, D at the second occasion, and then C, D, E at the third occasion. And if things are calibrated properly onto the same metric, then you can have growth in that latent variable, even though it's not measured by the same thing at each occasion. And that makes a lot more sense if you're measuring children or people who change quickly and you don't want them to ceiling or floor out on your measures. So to me, the real reason why you would switch to this SEM version of things is to take advantage of the measurement modeling capabilities, and then put your growth model on top of a latent variable. And that would be one of the advanced topics I would want to cover next spring when I teach the advanced longitudinal. Not to mention time-varying predictors, which case you would, you'd want to do it this way. One other reason why potentially you would want to do it this way is if you are thinking of these random effect latent variables as predictors of some other thing. So in the multi-level modeling world, these are Ys. We talk about random intercept variance in the outcome, random slope variance in the outcome. If you want to see like how change from, say, first to third grade predicts how well they read in the 8th grade or something like that, that needs to be an SEM. Because change is an outcome in multi-level models, not a predictor. So for any of you who might be asking yourself this question, what should I use for my data? I'm happy to chat with you. There's pros and cons to both versions. There's limitations to both versions. There's not necessarily one right answer for every case. But it's good to be aware of your choices. And here's what the picture would look like if you have a multi-level structural equation model, which is nothing more than several multi-level models estimated at the same time. It's all fancy marketing. All right, how's that? A quick overview. Quick questions before we call it a week. No? No questions? Fair enough. We're out of time anyway. Thank you for being here. Thank you for playing along, and work on your formative assessment, and I will be happy to see you next week. Bye, folks.